I think it started with the Pilotless Aircraft Research Division at Langley. After World War II, there were many surplus solid propellant rockets around. It was ordnance. They were not made for spacecraft or rockets of that sort. It was pure ordnance. Robert Gilruth got the idea that you could investigate the transonic speed range, which was virtually impossible to do in wind tunnels, but using rockets to propel the test models in free flight. Equip them with small radio transmitters, called telemeters at the time, and collect the data that way. He formed a division. It was called the Pilotless Aircraft Research Division. Max Fauger was there, Robert Pylan, Bill Stoney, myself, and there was maybe 50 or 60 eager young engineers that had come there. And this was a whole new technique for getting data. And it was wide open. You could do anything you wanted. They either purchased or leased, or the government had land at Wallops Island off the Virginia coast, just near Maryland on the eastern shore. And it was set up as a launch facility. And it was a terrible place. It was nothing but a marsh and a strip of sand, and it had a few Quonset huts on it, and so forth like that. And it was kind of living in the raw when you'd go up there to test things. But anyway, that's what started it. The first thing you know, these things that were supposed to explore the transonic region were getting hypersonic. And we had some vehicles that were getting close to escape velocities. And so the first thing you know, people started saying, well, if we just made it a little bit bigger and had a few more things, you could put a man in it. But more and more people got thinking about it. And I think that's what started the whole business of the space program.
You were flying under the banner of NACA during most of that time, weren't you?
Yes.
Before NASA.
Yes.
The
and then
Advisory
the
Council
transition was, when, 1958 or something like
58,
that?
yep.
58, yeah.
And suddenly there was something new called NASA,
yeah.
National Aeronautics and Space Administration. Wasn't that a grand name?
Yeah, that was a grand name. Of course, we were very excited and also worried because the Air Force was in that game too. And the politics didn't know for sure which way it was going to go, but the president finally decided it was going to be a civilian outfit.
And actually, you married the military in terms of getting some of those early boosters, didn't
you?
Both
yes.
Army and Air Force, now that I'm remembering.
In fact, most of them were Army.
Yeah.
Army.
Well, let's go back over those beginnings, because now we see the Space Task Group. Here's this new organization. It's NASA. You've just changed, and not your allegiance, but you've changed the flag under which you're flying. Yeah. And so now the Space Task Group is getting organized, and there you were at the very beginnings. What role did you play at that time, and how did it work?
I was a designer of these test aircraft. Roughly, the agency was set up in an administrative department, the research department, and then what was called the technical services. Now, all the people like the Fauchers and the Gilruths were in the research department. I was in the technical service. It was our job to perform a service, an engineering service for the research people. This included the shops, the instrument people, all that sort of thing. And so, in a sense, I was brought from the organization I really worked for to help these people. So that's how I became connected with the whole business.
Did they give you a title at that time? Because everybody in government service has a title.
No, it wasn't all that formal. I was a section head, as it was called then. And there were a bunch of young fellows. I think one of the things that made it go to is that we were all young. All the older people were in the wind tunnels, and this was a new game. And fortunately, it had a bunch of young people, because you can't teach the old guys a new game. And the wind tunnels, they were like the battleships. Yeah, and you remember in the services how the battleship world had a big fight with the aircraft world. And the old admirals didn't like these airplanes, and the wind tunnel people didn't like those of us with these pilotless aircraft doing the research work. And I think that had a lot to do too. That it was young blood. We didn't have enough sense to know that it was, it was going to be a difficult thing to do.
Seems to me, though, C.C., that at that time something big happened. You had been working with pilotless aircraft, and suddenly the mission had to do with sending a human being up into space, an unknown area, an unknown ocean, if you will. And how did that beginning come together? How did you begin to design something for a human being?
I don't know, except that obviously sooner or later, whatever you do, you're going to put a man in the thing, no matter what it is. I'm sure it's almost no point in doing things if a man is not involved sooner or later. And of course, by man, I mean mankind, humans, something like that. And I'm sure it must have first speculated about monkeys, if for no other reason they're smaller. Only weigh 12 or 15 pounds, and as opposed to 150 pounds, something like that.
Good idea, maybe, to test hardware on animals before you put human beings in the loop.
Yeah. In fact, there were a bunch of jokes about that in the Mercury days. In fact, I think I remember making a cartoon that something to the effect that, do you remember Sam, the monkey Sam? And he more or less just went along for the ride, but I wrote a memo and suggested that as long as he was there, if you could teach an astronaut to do this, you can sure go teach a monkey to do this.
I noticed you said you wrote a memo. You have a lowly opinion of memoranda, don't you?
I know. Well, that one was kind of a joke, and the crew people didn't take it as a joke at all. But
I wonder why.
I wonder why.
Where did the name Project Mercury come from?
I don't know.
Remember that? It's out of left field suddenly.
I don't know.
The messenger of the gods.
Yeah, I guess so.
With wings on his heels.
Wings on his heels.
Well, then along came the astronauts. 7 test pilots were chosen.
Yeah.
And they came into the picture. By that time, where were you in the design phase, by the time that the men came into the loop?
Well, let's see, 1958, I have a drawing at home of the drawing I made of Mercury, the first drawing I made of Mercury. We had put together a little paper and explained the systems, and I made the overall configuration arrangement. And that was dated June of 1958. And see, that's just about when NASA became NASA. So we were that far along before there was at NASA. And see, that was quite a bit before the astronauts came aboard.
What do you remember of that first design that you put together? Can you visualize it for us?
Well, in the first place, it was a pencil drawing, and it was not made with a computer. I'll tell you that much. And it was, I still have the original. For some reason, I kept it. And it's remarkably like Mercury turned out to be. It's a man in it, a retro rocket. It did not have an escape rocket system. That came along later. But otherwise, it's the same parachute arrangement, and it's the same shape.
Did it have a window?
Yep, had a little window.
Mm-hmm.
Yeah, and so it's not true that we didn't have a window in it.
The process of putting a spacecraft together has always been fascinating, and most people haven't the slightest idea of how you do it. So here's your chance, CC. Tell us, how did that Mercury spacecraft come into being?
Firstly, the guys in the research business in the Pilotless Aircraft Research Division had found out that, of course, that there's a lot of energy has to be dissipated when a spacecraft enters back into the atmosphere, that the blunt body was the most efficient way to do that. Everyone else had always assumed that things should be pointed. And it turns out that the blunt body is really the better way if you just want to brute force something. You can decelerate yourself with the least amount of trouble with that blunt body. Now, with the blunt body, it turns out that the force vectors are such that a man can lie on his back across the craft. When things have a point, you cannot, it's hard to fit a man into the little thing that's got a point. Second place, it was obvious from all sorts of tests the Air Force had done that men can sustain accelerations better, more or less, what's called eyeballs in. That the forces are in, like you're lying on your back. You put that together with the blunt body. Then there were parachutes available that's quite dependable, parachutes. We had a lot of experience with these solid propellant motors that you could do the retrofire business to slow yourself up so you could re-enter the air. So suddenly we had all the fundamental elements that it took. Now, then it's just up to someone to shape these things together, package them, and arrange them geometrically so that all these things fit. Well, that was essentially my job, was to package all these separate elements that other people had worked out and selected. I never selected a rocket motor for it. I never selected the kind of parachute. I didn't design the initial heat shield for the thing. Other people did it. But I took all the things they did and put them into a package. There's an English word that's difficult to pronounce. It's called consincity. C-O-N-I-C-C-I-T-Y, something like that. And it means an artful arrangement of things. I would use the word more often, except it's so difficult to pronounce. And so that's what I tried to do, make an artful arrangement of systems.
Once they came aboard, did the astronauts have anything to say about all of this?
Well, they were probably in a state of shock too at the time. I'm not quite so sure they must have looked at this thing and thought, my God, what have we gotten ourselves into? Because it's the first place, it doesn't look like much if you look at Mercury. It doesn't look like much of a thing.
Not if you're used to flying high-performance jets.
That's right. But they didn't come in roughshod and try to throw their weight around.
The image that has been presented in books and motion pictures gives somewhat of that idea. You're contradicting it.
Oh, that's not so. They were sensible enough to know that different people have different skills, and their skill was flying airplanes. It was not designing airplanes, and not that they could have learned to do that too, I'm sure, because they were very intelligent, capable guys.
Well, Mercury, of course, was designed to put a man in orbit, but you also designed it so that it could be remotely controlled. You could eliminate the man from the system if you had to.
Yeah, that was a running battle throughout the program. There were those of us that say, why should we waste 150 pounds in worrying about all the safety of a man when with a quarter of that weight you could automate the system? On the other hand, people would say, well, what's the sense of doing all of this if the man is not involved? Sooner or later, the man's got to be there. Unfortunately, this system got polarized. I don't mean within the Mercury program itself, but if you remember, NASA finally divided into two camps, the manned and the unmanned systems. And, there's a place for the marriage of the two. There's some things the men do wonderfully, and some things they're not very good at. The instruments can do things great, but some things they can't do worth a damn. They can't think, for one thing.
The Russians followed a different tack. They said, okay, we want this automatic control. And to this day, they still have it.
Yeah.
As they fly their cargo vessels up there to replenish the Mir space station. Do you think perhaps that might have been a better path to follow in retrospect?
Well, it would seem like it's a sensible thing to do, since there are many missions that there really isn't any point in having the man there if it's simply a resupply mission. Or let's say, turn it into reverse. It's just a shuttle type of thing going back and forth as routine. And that's one thing that the men don't do very well, or routine things.
So there would be a place for unmanned cargo craft.
Yeah, I would think so. I certainly think so. For instance, the docking activity. It's easy to automate the thing. the total navigation system. Well, obviously, we have all sorts of unmanned satellites doing all kinds of things in space.
You were working with Max Faget, were you not?
Yeah, oh, yes, very closely.
He was designing, you were taking the design and putting it, as you say, into artful form. I understand that you even designed portholes, no windows, in the original Mercury. Is that right?
It was a port. Yeah, I suppose. I'm not quite sure the difference between a porthole and a window, except the porthole is generally small and the window is large, I suppose you might say. But, and if you remember, Mercury ended up with a thing called a periscope, and it turned out to be not a very satisfactory device. But, you know, it was clear that the man, he's got two eyes, the best instruments there ever were. Those two eyes, and to deny those eyes a port to look at is kind of silly. That same thing came up in Skylab years later. It's that same argument.
A lot of navigation aids also called stars.
Yes,
if you can see them.
Yeah.
The Mercury interface between the capsule and the rocket was a big contribution. I understand that was a matter of some concern for you. Was it?
Yeah, yeah.
Can you tell us about it?
Well, at that time, the only candidate launch vehicles were things like the Redstone rocket and the Atlas. Neither one were designed with the idea of putting the Mercury on the end of the thing. So they were designed to their own particular requirements. We had a heat shield that was vital to the thing that really wasn't the best thing in the world to be the interface or something. And so it took a little finagling to make these two completely separately designed objects. Take the loads, make certain it's separated when it was supposed to, and not separate when it wasn't supposed to. And so there was a lot of mechanical engineering involved in the thing that you might say had nothing to do with the spaceflight business itself.
Had a lot to do, though, with the way that thing flew.
Yes. Yeah.
How did you come up with that design?
Well, we had been, in the Pilotless Aircraft Research Division had been doing that all the time in a smaller way. We had ordnance rockets, and then we had the test vehicle that went on the front, and they had to be separated after they did the thing. And so we had a chance to explore a hell of a lot of different ideas. Some worked and some didn't work. That was another thing that we found in the Pilotless Aircraft Research business, that people didn't know a hell of a lot about the aerodynamics of hypersonic flight. But we found out the hard way that things that had funny shapes, asymmetrical shapes, were more prone to having trouble than things that were more or less bodies of revolution. So we stuck with those bodies of revolution for a long while until the shuttle came along. If you notice, everything was essentially a body of revolution. And there were a lot of us that were very much worried about the shuttle, since it was so clearly not a body of revolution.
Obviously, we're going to get to the shuttle a little bit later. Right now, let's stay with Mercury for just a bit, because here you had a spacecraft that finally was conceived, and you flew it on a Redstone rocket, suborbital, testing your wings, as it were, even though there were no wings on that spacecraft, obviously. Did the spacecraft evolve at all during the Mercury days, or did it pretty much remain in the same design for all the flights?
Initially, it changed a little bit, but by the time it got to actually be flown on the Redstone, things had settled down, and there were very few changes of consequence then. That is, you couldn't look at it and see any great difference. There had been problems. There was a series called the Little Joes and the Big Joes, and they were called boilerplate things, designed just to test certain performance characteristics. Now those flights, and they were unmanned, of course, suborbital, but they revealed a number of surprises. And that was, it was very important because we caught the thing at a stage of design that you could change you might say the production article without a great deal of cost and trouble. And of course there was no man involved in it either.
Can you elaborate that point for us just a bit? What
yeah, if you can remember the shape of Mercury, it was essentially a cone, except where the apex of the cone would be, it ended up a cylindrical section. If you can remember, the side sloped up and everything. It was bulged like that because to house the parachutes, for one thing. There just wasn't enough space in this point to house the parachutes. We miscalculated the heating effects of doing that. It turned out that the sloping sides of the Mercury were relatively cool. But when that changed in direction, suddenly instead of sloping sides of the cylinder, it got very hot there. Much, much hotter than anybody had anticipated. And we had to change the skin of the thing. We found out that it was completely inadequate. Now, Big Joe found that out. I remember that when we got it back, we had burned some holes in the side. Actually burned all the way through. And it had survived, though, but it was obviously needed to be redesigned. But some flights like that pointed out a number of things. The stability of the system was always some question.
You say it was some question, but the stability obviously was sufficient.
Whether this blunt body shape would work. But do you remember there was a Big Joe flight that it did not separate from the Atlas initially. What happened was the Atlas continued to thrust when it was not much, but just enough that when the Mercury tried to separate, the Atlas kept pushing. And the Mercury spacecraft used up all of its control gases trying to turn itself around to enter the atmosphere in the right direction. But it was still being pushed by this great monstrous Atlas. And it wasted all of its gas trying to turn the whole system around, and it ran out of gas. And finally the Atlas gave up and fell off too. But now Mercury was heading in the wrong direction to come in, with no control system to turn it around. But it was inherently stable in the other direction, and it turned itself around. Now, we were absolutely delighted at that, because it was unexpectedly more stable, on-point stability than anyone had thought. Now that's a very satisfying feeling to know that if you ran out of all your control gases, the damn thing was going to turn around the right direction anyway.
Wasn't that the real reason for the ballistic re-entry itself and the shape?
Well, the real shape was to take care of the heating problem. Now, it was theorized that it would be stable in this position also, but there were a lot of people that would not have thought you could become 180 degrees wrong and then turn yourself around. But it did.
Like I shot an arrow in the air. It came back to Earth. I know not where, but it came back to Earth.
That's right.
That's really
and they come down point first because you've got feathers on the back.
Well, finally, with Mercury, then, you realized you had a machine that could take men into space. But something else that had to be learned: how would the man react inside the spacecraft? Did you follow those flights?
Well, of course, it's just a small group of us, so everybody paid attention to everything. But that really wasn't my bag. I didn't design life support systems. I was interested in the physiology of the man simply because it was a mechanical system as far as I was concerned, and he had to be supported mechanically. And so I was interested in the body structure and how the couch should be made and that sort of thing. And of course the man had to be positioned properly in the spacecraft.
Yes, if I remember correctly, C.C., as Mercury really began, somewhere shortly inside that envelope, the president announced after Shepard's flight that men were going to go to the moon.
Yeah.
And I imagine that created a few changes back at Langley, didn't it?
It sure as hell did. Now put your money where your mouth is.
How did you accept that challenge?
I don't know. If I knew then what I know now, I think I'd have gone to Australia or somewhere to got the hell out of there. But I don't know.
But you didn't. You went ahead.
I don't know. I think that's a good thing about being young. You're not, nothing frightens one when you're young. You know, you can lick the world.
Anything's possible.
Yeah.
And in this case, it certainly was possible.
Oh, yeah.
How soon did you begin designing on Gemini coming out of Mercury?
I personally didn't have much to do with Gemini. Gemini was really an outgrowth of Mercury. I mean, it's an extension of Mercury. McDonald was already set up, and the people that were working on it, and they had learned a lot of things about spacecraft and Mercury, and the organization that did Mercury was all in place. I'd really never had much to do with things once they got into the factory. Once the job would, say, be turned over to McDonnell Douglas or whoever.
Wasn't the big thing, though, the big difference from your point of view, the fact that Gemini was designed to dock with other objects in space, and that's where you came aboard and said, okay, let me go to work. Yeah,
except even then. I'm surprised now in telling you this, but I'm surprised that I was not involved, didn't involve myself in that. I think the reason was that we had started Apollo. You see, we were working on Apollo before Alan Shepard took his flight. And so, as far as I was concerned, I was deep into Apollo when Gemini was being developed. Now, as it turned out, I wish I had paid some more attention, because some things happened in Apollo that were led by Gemini. For instance, the docking system had a lot to be desired. And it ended up that Apollo inherited some of the concepts from Gemini, which was not a very good system. At Langley, it was formed after World War II, and it was going to exploit some ordnance that the military had developed for essentially solid propellant rockets, which were used as missiles. They were available, they were cheap, the Army had more than they knew what to do with. Robert Gilruth and perhaps some other people decided that it might be a very effective way to do research, aeronautical research, in the transonic regime, that is just below and just above the speed of sound. Wind tunnels had a very difficult time at the time coping with that particular speed range, and so there were very few data available. They formed this pilotless aircraft research division to exploit that technique of building models, launching them from Wallops Island. They acquired that site out over the Atlantic Ocean, and using telemetry and tracking radars to acquire a great deal of data. And it started off with, I don't know, there's probably were a dozen people recruited from different places at Langley. And all the engineering people, for the most part, were very young men, just out of the Army. People like Boucher, he was from the Navy, but a fellow named Thibodeau was his buddy, and they both were from Louisiana, and he had just come back from Burma. I just picked those two, but these were young engineers that were eager beavers and bright and really wanted to do something. I had already been working at NACA at the time. This was before NASA.
Okay.
And I was working in the engineering side of the house, not the research side of the house. And it was a part of the organization that implemented concepts that were got the machines built and the equipment built to use by the research people. And it takes both sides. And then the shop fabrication types of people formed the third group of people. So there were the people, the research engineers, the design engineering people, and then the shop people. So it was a little close-knit group of people. And in the course of doing that research work, velocities of these craft were getting higher and higher and higher. And we were finding out more and more things about heating and the re-entry into the atmosphere, because they were practically going out of the atmosphere before they entered. And somebody says, why don't we put a man in one of these things? We're damn near orbital speed.
Do you remember him?
And he'd say, yeah, big deal, something like that. And pretty soon it started to get more and more serious. The management was certainly aware of it, but there was no mechanism that I know of in the agency to officially begin a project like that. You can't, Golden can't just up and think of a whole new thing and say, let's do it. It's just politically impossible. So what you do is the group of people interested in it start kind of faking their time sheets. You charge it to something that's chargeable, but you're spending some time working on it, and the management agrees not to look too close. They know what's going on, and they sense that it's a good thing. And finally, you get it to that place, between guys like Fauché and Matthews and maybe John Disher at headquarters. Only a few people kind of knew about this. And the first thing you know, there's enough data to get everybody's attention. The Air Force was in the game. They were doing their things too. Mm-hmm. And there was kind of a competition going on. And I don't know, I can't remember exactly what happened that it was finally gelled into a recognized formal project. Mm-hmm. But somewhere along the line it happened. And it all came about through this informal evolution of an idea. Mm-hmm. And I've thought of it since then. One time there was a group of people at Johnson Space Center. They were called the Advanced Projects Office or something like that, new projects or something. And they were formed not because, this doesn't sound very nice, but not because they had any great ideas about what to do, but they didn't have anything else to do. And the center said, we ought to have a new projects office. So they picked these people and said, you're the new projects office, invent a new project. Well, they didn't have the foggiest notion how to do it, of course. And so they asked some people, myself included, they said, how do you get started? And I told them more or less what I just told you. They didn't believe it, and they just walked away, paid no attention to it. Because there just was, a thing like that emerges from the ranks. Mm-hmm. If there's a good idea, it gets developed because somebody's enthusiastic about it, and a lot of them die. Some of them are not good ideas. Only 1 in 1,000 ever gets through. You can't just pick some people and say, go off and invent something. Mm-hmm. Right. You've got to wait till somebody does it, and then you do something with it. Mm-hmm. I think that's the way Mercury started.
Really?
I'm sure it started that way.
Now, do you know who came up with the idea?
Well, of course, the Russians were in the game too, and pretty soon it was pretty clear that other people were working on the same thing, and that was a desperate attempt to be the first to do that. It's remarkable how close things came out to be. Gagarin's flight and Shepard's flight were only months apart, and you would think that, given all these years that we've been in the aircraft business, and that it seems kind of strange that two big events like that to come within a couple of months of one another, as opposed to years apart.
Right.
But anyway, that's the way it happened.
How did you get to Langley?
Well, I was born and raised in Hampton, and that's where Langley was. And I don't think it was inevitable I'd end up there. When I was a kid, the neighbors, several of them were young engineers that had come to work for Langley, and I would hear them talking about things, and sit around and listen. The families were socializing together, and you know, I somehow or another I knew that's what I was going to end up doing one way or the other, and talking to these guys, and of course they would help too. If they noticed some kid that showed some interest, they would go out of their way to, you know, I remember one time one of the guys invited me to come to Langley. He had to work, but he introduced me to a couple of people that let me sit around and watch things that were happening, you know, and then he picked me up at the end of the day and took me home. And that was, you know, a big deal, boy. That was a big deal. So that's how I happened to be there, and worked it all right for me anyway. Yeah.
And now let me ask you a little bit about Mercury itself.
Okay.
How did you actually start designing it, or what ideas were thrown around to design something that would hold a man on top of a rocket?
Well, first off, part of the research that was going on between a man named Bill Stoney and Robert Pylon and Max Vauger involved one of the problems was re-entering the atmosphere. And a great deal of heat is generated in braking. You can't slow something up without something happening. You know, you've got to absorb all that energy somehow. And it was enough to melt metals. The Army was dealing with it with ballistic missiles, if you remember, and they were developing one shape. And in the course of this research at Langley, of all things, it turned out that a blunt face, the Mercury kind of blunt face, you would think that's a horrible way to enter, that you really should have a nice point. The trouble is with something pointed, it doesn't have much drag, and it keeps going fast a long time, and it gets denser and denser atmosphere, and it just gets the situation worse and worse and worse. The best thing to do is slow yourself down as quickly as you can while you're still high, so that you can dissipate the energy at that point instead of getting so hot. And this blunt body did that. And it would get so hot that a shield of gas around the front of the thing almost essentially insulated it. And it kept shedding that. All the hot air was hitting this one little place, getting so hot right on the surface it was re-radiating its heat back out. And so everything considered, it was a far superior way to enter. Now it turned out when you got that blunt shape, all of a sudden now it was reasonable that you could put a man lying on his back with his feet kind of up like this, and it doesn't take such a big thing to do it. If you notice the pictures of the Mercury, you know, that thing was only 6 feet across, and the man was almost 6 feet, but by the time he drew up his legs like this and sitting, you see. And all the G-forces, that is acceleration forces, are on your back. That's why you saw the pig and that couch on your back. So see, it all worked out exactly right. It all came from doing the research work and devising this blunt body concept. And that's persisted on the spacecraft as a better way to do it up until the time of shuttle. Now the downside of it is that it cannot land on the Earth without a parachute or something like that. That's the downside. But the real thing that made it was the fact that it could survive the heat of entry into the thing. And that came about just by these several young fellows exploring this regime and using their heads, and they came up with that. I would like to claim some credit myself, but I can take no credit for that, I'll guarantee you.
Well, now from what I understand, some of those people came up with the data and realized what they wanted to do, but you were the one who translated that onto paper.
Well, yeah, in a sense, that's just about what I did. I took their ideas and the concept and would simply reduce it to a geometric presentation that you can understand. And of course there's some practical things. You have to fit the people inside, and you've got to get the parachutes in there and all the other paraphernalia, and so it takes two sides of the thing. But we never worked like this group here and this group here. It was just kind of like this. There was no doubt that the flow went from the research people to people like myself, and then to the shops. That was the direction that things moved. But all of them were just like that. There wasn't there and here and here, and there was not a big paper transfer from here to the other. We all worked in the same building. And so it was just a matter of, you just talked to one another. And after you do that a while, first thing you know, you understand what the other people are talking about without having to write a lot of paper about it. Unfortunately, the world is no longer that way. It's now nothing but a big paper trail between everything. The downside of that is you have a hard time tracking it because there wasn't any paper left. That's the downside of it.
How did you communicate between, as you called it, the shops and as well as management? And how did those ideas come across for Project Mercury?
Well, the management consisted, as far as I know, of about, I shouldn't talk about that because I didn't penetrate the top management, but there was only not people like this on one hand. The Washington headquarters just almost purposely seemed to stay aloof of the thing. I think they were frightened that it would. In fact, Dr. Dryden, he was a good man, but he said it was just a stunt. There's of no practical significance. It's just a stunt. And I think they were politically frightened that it would turn out bad, and then they would get smeared with this thing. That. So I believe it was people like George Lowe. I think he and John Disher. There may have been more at headquarters, but those two guys, as far as I know, were the only guys at headquarters that ever seemed to pay attention to it much. Abe Silverstein was involved in it a lot, but he was at another lab, the Cleveland lab, and it seemed like the different NASA NECA centers, the same rivalry went on then as it does now. They were not. One center was not very enthusiastic of something the other center was promoting. They didn't fight it, but they were not very enthusiastic.